Okay, I think I made the right. I jumped in the wrong Zoom, but I think I'm here now. This is Brett.
You are here now.
Are you on multiple channels?
Of course.
Zooms? All right. All right. All right, so I just do the share thing.
Okay, we are already live on YouTube, and so we just need your screen share, and then you can go ahead and start at 11 o'clock.
All right, sounds good.
Somebody who is unmuted has some background noise, so if you're not presenting, please mute.
Okay. Can y'all see my
I see it.
all right. All right. Do y'all see just the front slide, or I see like a presentation view also.
Sequential consistency in Perl looks good.
All right. All right, should we kick it off?
Yeah, I think it's after 11. Go for it.
All right. Well, thank you for attending this talk. This is a topic that I have been thinking about for many years, and hopefully you'll find it as interesting as I do. The slides, it's a simple concept, and but it's got a lot of background, and it was hard to kind of put this in a unified way. But before we start, I wanted to mention I work for cPanel, been there for about a decade now. And I'm also a member of the Houston Perlmongers. And we do Zoom things by Zoom most of the time now. And we often get visitors from other PMs all over the world. And y'all are most certainly welcome to join us. That's our website. And anyway, looking forward to seeing some of y'all there. We've been talking about some pretty interesting things lately. So, okay, a little bit of history. So in 2006, I pushed a module to CPAN. It was pretty much my first major module, or maybe my only major module. And it was a result of basically a homework assignment that I was working on at the time. And I was exploring regular languages, finite automata, and the homework assignment was to write a program that would convert a regular expression, and now I'm talking about regular expressions in the formal computer science term, into a deterministic finite automata. And that spurred this toolkit that, because I wanted to look at different, what kind of DFAs were created by different kinds of regular expressions. And I had been into Perl for a few years at this point, and it was a natural fit. It is a really interesting module, and some of the stuff that I was digging into was very interesting to me, but I didn't use it for anything other than messing around until recently. So it's been sitting on CPAN for about 15 years. And I have interest in concurrency. There's always been interest in concurrency in the Perl world, but there's always been a sticking point related to the fact that the Perl runtime process is a single process. So recently, I thought maybe I could utilize some of the capabilities of this flat module to explore that topic a little more. So I'm talking about Perl in two different ways. There's Perl the language, and I'll use that capital P, and then there's the Perl runtime, or the interpreter. Okay, the Perl language, and I'm not going to show examples, but I think we can all agree there's a strong temptation when somebody is learning Perl and doing all of the cool things we can do with the language and the semantics, to want to do things concurrently or in parallel. There's nothing inherent about Perl, the language itself, that makes it have to be run in a single process or sequentially. And that's for a variety of reasons, but I don't think anybody would argue with that. Perl, the runtime is unforgivingly single process. And I know this because for 20 years now, I've been one of the people who, will chime up every once in a while and say, why can't we have, real lightweight shared memory threads in Perl? Why can't we do things in a parallel way? And my background is in high performance computing, and I got into message MPI, message passing interface. One of my favorite things to play with though is OpenMP, which is a high level declarative way to interface with threads, and a lot of times that those threads are implemented with P threads. In any case, my strong interest was in shared memory parallelism. So now I also care a lot about the Perl community, just like everybody else here. And there's always something nagging at me about why were there always people asking for this, for parallelism or threading, or I say I'll call it real threading, and then somebody will get offended. But when I say real threading, I mean real lightweight threads where processes can use shared memory, not what's provided 4x4. So, but I accept that that's the case. And once I fully embraced the fact that the Perl runtime is a single process, it is sequential, then things started opening up for me. Now, one of the problems I had was, at least for me, it was forcing me into a state of cognitive dissonance. You want to write concurrent or parallel things using Perl, the language, but you can't. So then there have been these Herculean and heroic attempts over the years to provide some sort of parallelism, or what feels like parallelism. And this has been exacerbated by the fact that multiprocessors are on everything now. So ultimately the purpose of this talk is my attempt to reconcile what I want to do with Perl, the language, and what I am given as far as the single process that is the Perl runtime. So a little bit about shared memory concurrency. Communication is implicit. It's done over shared variables. And it, as opposed to, say, a message passing type of approach where you have a bunch of, say, sequential communicating processes that are communicating actual messages in an explicit way. I mentioned MPI earlier. This is what's typically used on these large Linux Beowulf clusters when you have a bunch of processes running across a cluster. So you've got these compute nodes that have more, have many CPUs within a shared memory that share the same memory, and then they're all connected over some kind of network that facilitates communication. So like Ethernet or InfiniBand is another one. So in any case, but in order to quote unquote share memory, or to allow participation in some collective computation, let's say, MPI programs have to send over messages, and the messages are usually data structures, and MPI is great. I really think it's cool, and it does it in a very efficient way. But that's not what I want for Perl, or what I want. That's not how I want to be able to program in Perl when I talk about concurrency. And I also prefer the SMP approach, it's symmetric multiprocessing or shared memory programming. I use those terms interchangeably. So one of the benefits of shared memory concurrency, and since the communication is implicit using the state of memory or a variable, is that you don't have to explicitly communicate. You can implement algorithms and computations in a very implicit way. And I think we all know with Perl admits a lot of implicit approaches, meaning that it's much more of a functional or declarative approach to what you want to do, as opposed to how you want to do it, how you want to implement the low level protocols in place. So that's another reason why I like the shared memory approach, because I'm lazy, and I think a lot of us are. So there's value. The ultimate point of, I think, all of this is there's value, at least for me, in presenting a shared memory type of approach, even if where the program is getting executed happens to be a single process. And that's where I'm going with this. So I'll put it this way. I want to have all the fun of traditional shared memory programming, but inside of a single process. And that includes potential for race conditions. That includes opening up all of those pitfalls that shared memory program gives us. And I want to be able to do it naturally within Perl, or as naturally as possible. So the nice thing is that Perl, the runtime, since it's a single process, has a very well-defined and safe and consistent memory space. The other thing that I think is pretty exciting about being able to do this within a Perl process is the ability of us to make subroutines stateful using the state keyword. And I think that although you can use closures to affect that in other ways, having this easy ability to give state memory or the subroutines memory from call to call, basically making them coroutines is super powerful, and that frees up your mind even more to do some interesting things and think more about the problem and the solution that you're trying to solve. Okay, so this is a motivating example. I'm not showing the rest of the Perl here, but the approach that I get into towards the end of the talk is basically defining an execution plan, and I've been calling it a plan, that take where the words in this example, this is just a string, but it describes that how the subroutines that I will define relate to one another. So, and I'll get more into this, but you can look at, so begin, the capital J, capital A, capital P, capital H, and then the end, those all represent defined subroutines within the rest of the Perl script that I have not yet shown. So I will be explaining this later, and hopefully this will keep you paying attention. So a few, more than a few terms that I'm going to be talking about is Uniprocess. What is that? What is a memory model? What is sequential consistency? I'm going to talk about finite automata, although I don't go into a lot of depth. It's a super interesting topic, and I could probably talk to you for hours about it, but this is definitely not the place for that. And then regular expressions. Now, when I talk about regular expressions, I want to be very clear. I'm not talking about Perl regexes, although I believe the Perl regex engine utilizes the concept of finite automata, but it's a whole lot more powerful. So I'm definitely not talking about Perl regexes here. I'm talking about the formal concept of regular expressions within the confines of formal languages or finite automata within computer science. And then finally, I'm going to talk about, I'm going to define what the shuffle operator is. And I'll tell you right now, it is an operator that sits right next to concatenation, the union, and the clean star. And it's an additional operator that I don't think most people really have heard of, because it really hasn't been that useful. But I think that it's useful for what I'm doing. So Perl is a uniprocess. Perl 5.0 came out in 1994. At that time, not even Linux was supporting SMP. All the machines that we had were single process, or at least the ones that we had at home were single process. Nobody was really thinking about, utilizing all of the computational power that might be on your desktop. And certainly people were not thinking, how can I express something that has parallelism or concurrency, but then run it correctly in a single process. So there was no reason for Perl to even consider being anything but a single process when 5.0 came out. And that, I believe that's a good thing, because a uniprocess or single process environment, processor environment or single process, that gives you a lot of power because it inherently is shared memory. You're sharing memory among one process, one line of execution, but it provides a consistent memory. When you're programming SMP, you have to consider the state of the memory. Memory can get corrupted if two threads are updating it at the same time if you're not careful. And it actually, it actually is easier to just assume that you don't have all of those pitfalls. But at the same time, it allows you to maybe think in an SMP type way for the day. Let's say that you do have a true multi-process environment or runtime. So within Perl, there's been a ton of workarounds. And I don't like any of them. I'm talking about iThreads. I'm talking about anything that says it's threaded Perl or it provides threads. Ultimately, if it's not limited to the confines of a single Perl process, then it's necessarily using the fork system call. And I like fork. I'm a big fan of fork. I distribute large workloads using fork. But what fork doesn't give us is a way to generally share memory among the processes or the children. And again, there's been a ton of solutions to this, but they're file based. They're messy. They don't give us what we really deserve in terms of threading or SMP support with respect to Perl. It really hampers our ability to think and be creative. But again, I totally accept the fact that this is a uniprocess, and I've really come to embrace it. And again, I'm going to mention there's been a lot of negativity. This is one of the areas where I guess Perl fights tend to happen, and it's in my opinion, and I don't think anyone would disagree, the more that we can just embrace the true state of things and see what we can do within the limitations of them, the better. The more that we can all work together and focus on providing interesting solutions, which is what the Perl community is absolutely known for, and why I love it. But one of those things is threading, or is providing some sort of concurrent semantics. And I think that to a large degree, when people want concurrency or they want threading, they care more about being able to express their program or their algorithm in this way semantically, rather than the actual speed up of the program. Speed up of the program is important. I would love to use bare metal machines that have 16 or more processors. That's the kind of thing that I like to do. But in any case, what I walk away with when I've written something that uses in an SMP style is I just think it was a pleasant experience, and I don't have to think too much about making sure that was correct beyond what was necessary. So I say there's a silver lining to this, that we can just start with, all right, we've got a single process, but we want to write things in an implicit shared memory way. This is kind of how I think about it. I've got on the left, I've got a big old bulldozer, which is the Perl runtime. And then on the right-hand side, got a bunch of all these, bunch of efforts trying to do things in parallel. It really can be seen as a boat anchor, but I've more or less moved on from this point of view with the work here. So I'm going to talk about sequential consistency now. Sequential consistency is, and I'm not going to read Lamport's quote here, but I absolutely recommend you read the work of this man. He works at Microsoft Research. He's the creator of the Byzantine general problem. He is, I think he just won a Turing Award, or one of the top computer science awards within the last few years. But he has some very interesting work, and he came up with this term. So the way I would describe sequential consistency is, say you had you had an algorithm or program that did things in a parallel or concurrent way, and you had multiple processors on which to do it. Well, say you went from multiple processors to one processor. Well, necessarily you would still have to do the same amount of work. A lot of that work has been defined in somewhat independent ways, but you need to be able to collapse that parallel work into a single line of execution. And the question about sequential consistency is, how do you do that in a correct way? And we'll talk more about that. So some more benefit, I guess, I think I already talked about this. Benefits of Uniprocess is inherent memory consistency. There's no actual race conditions, although you can program them in, certainly express them semantically, but there's going to be no corruption resulting from them. We have, and this is certainly true in Perl. Perl has powerful runtime memory introspection. Perl in particular has an extremely well-developed capability for different types of scoping. Package scoping, file scoping, block local, and then stateful subroutines, as I've already mentioned. And there's probably more that I don't even know about. But those are extremely powerful, to the point where I will try to use some other language, and it will feel incomplete, because I want to be able to use the scoping rules that I'm familiar with, and sometimes I can't. Which is why I usually don't ever use other languages. And I've even extended my thought process to claim that the Uniprocess Perl has more in common with the Uniprocess operating system. And what I mean, I should probably put together a talk at some point what I mean, and maybe further develop that concept. But there's the Perl runtime, which is like the user land, and then we've got the core, which is the kernel. So I look at Perl as an ecosystem more as an operating system than strictly as just a language or just a runtime. And I don't know, some of y'all may get that joke that I made. Perl is an operating system that lacks a decent programming language. That's an Emacs joke, I guess. Anyway, moving on. Okay, so Perl's memory model. First, what is a memory model? And this is a Wikipedia quote. It's the interaction of threads through memory and their shared use of data. So it's given your computing environment, how does your program manage memory among multiple processes or lines of execution that are using the same memory? And that has a lot to do with the assumptions that you can make when you're programming in a shared memory way. A lot of it has to do with, how does the operating system handle caching? How does the underlying hardware handle caching? Is it the architecture NUMA, so non-uniform memory access? Is it CC NUMA, which is cache coherent non-uniform memory access? So terms like, when you talk about memory models and shared memory programming, things like NUMA come up, things like cache coherency come up. The different there are classes of algorithms that are oblivious to layers, to levels of cache, which is another interesting topic you may want to look into. This has nothing to do with it, but It's called cache oblivious algorithms. Always thought that was pretty neat. But that at least shows you that the memory model, the caching model that you are forced to use either through your hardware or through the programming environment has a lot to do with the assumptions that you can make. Well, since Perl is a uniprocess, we don't have to worry about any of that stuff. Okay. So when we talk about memory model within Perl, like I said, we have a single line of execution that is managing memory. It's a view of memory through the variable scoping facilities that Perl has. And this also has to do with data isolation, so block scoping. If you want to localize something so that you can, like say you want to localize the environment, the environment hash, the global environment hash in the runtime, but you don't want it. You only want to muck with it within a certain block. You would use local, that sort of stuff. And then ref counting is certainly has a lot to do with that because of the garbage collection aspect of Perl and the nice things it does for us, so that we don't have to worry about allocating, deallocating, freeing memory, those sorts of things. And that all has to do with Perl's memory model. But it all happens within a single line of execution. I believe there is one gotcha, and I think it has to do with the destructors. There's no, for example, you can't, if you have an object and you've defined a destructor method, or is it destroy method? In any case, that gets called when the reference goes out of scope, but you can't actually schedule when that happens. So as far as I know, that's one of the few danger zones in Perl with regard to its uniprocess memory model. But that can be managed. And then the other interesting thing I've mentioned, and I think that this is probably one of the coolest features of Perl, is that it has an easy way to give subroutines stateful memory, turn them into coroutines. So, in addition to all of the wonderful ways that we can dynamically create and define subroutines, we also have this mechanism so that we can give subroutine memory so that it can remember things from the last time it was called. And I think that that's very powerful. Being able to track or to remember things is it's one of the characteristics of increasing power, computational power, for example, from a finite automata which has 0 memory all the way to, say, a Turing machine which has random access memory. And then there's the push down automata that's in between, and another one, but I'm not going to get into that. In any case, memory in computing, memory equals power. And even though it doesn't give us additional computational power, because we're running, we're in a programming environment, we have Turing completeness. It gives us the ability to be more implicit. So we have to define things less, or we have to write less code if we've got things like subroutines that can remember from call to call. Okay. Performance. I mentioned performance earlier. We're running in a single process. There's no speed up. Most people, I think I'm contending this. This may or may not be true, but it's true for me. I would prefer to be able to write something concurrently or implicitly than get some actual speed up. Although speed up's really nice, and I love the idea that I'm actually using all the CPUs on my computer. But we're not talking, and what I'm talking about here isn't giving us any of that. It's not creating actual threaded Perl. It's not leveraging fork to utilize additional CPUs to distribute work or any of that stuff. What I'm talking about is simply giving us a way to describe concurrency while we are programming. But what this may offer some opportunities to provide some actual speed up, or to provide some avenues that maybe have not been possible or easily accessible up until now. Let's see. I said most of this. So some issues with SMP programming that are actually done using competing processes. There's real system resources you have to worry about. There's your disk I/O. There's network. There's a potential for corrupting memory. There's potential for overwrites, although what we're doing here doesn't save you from that one. But aside from the fact that we're running in a single process, we get a lot of safety in the fact that there's no real potential for unsafe things to occur. But we have not taken away a lot of the benefits of being able to think of how we're programming or scheduling or defining our execution plan in a concurrent way. All right, finally a picture, and most of it's pictures from now on up. I'm watching the time, and we'll try and get through all of this. So this is a program. It's not implemented in any way, but this is my attempt to show a true multi-threaded program. You've got CPU 1 and CPU 2 there, and then you've got the two threads. Each thread consists of, say, three operations that are dependent on the one that precedes it. So in CPU 1, you've got the thread where task A has to happen before task B has to happen before task C. And the same thing with CPU 2, and you've got task X, Y, and Z. There's a total ordering within each thread of those tasks, but there's no dependency between any of the tasks on CPU 1 and any of the tasks in CPU 2. And this is called a partial ordering. And there's no dependency between A, B, C, and then X, Y, Z. But there's a total ordering among A, B, C, and then there's a total ordering among X, Y, Z. So those are two. That's the kind of ordering tells us the kind of constraints we have if we wanted to, serialize this, go from 2 CPUs to 1 CPU. This is just pretty much what I said before. Oh. So I do talk a little more about total ordering. So A must precede B, B must precede C, same with X, Y, and Z. Partial ordering is exactly what I said before. The tasks in the set ABC have nothing to do with the tasks in X, Y, Z, and they can happen in any order with respect to one another, as long as the total ordering within the thread is respected. So what if we wanted to go down to from say 2 CPUs to 1 CPU? Well, you can call it sequentialization, you can call it serialization, you can call it linearization. But the point is, we want to be able to say, take the implicit ordering that may happen among the partial ordered tasks that are operating over 2 CPUs and put them in a valid form if they were to occur in a single CPU. So the top graph is the one I was showing before in the last 2 slides. The bottom is what a valid, one of many valid execution orders would look like if you went down to 1 CPU. And this is the obvious one. It's every ABC happen and then XYZ happen. But the important thing to note is we're maintaining that total ordering that was defined before among A, B, and C, and then X, Y, and Z. And at the bottom, I've got, you'll see it's like a string, right? It's A, B, C, X, Y, Z. That is defining the execution order, a valid execution order. In fact, this is all of them. If you were to enumerate all of the valid ways that you could combine this string down to 1, where ABC respected its total ordering, and then XYZ respected its total ordering. But then you can mix up anything from the first set with the second set in any order. Okay, this is what you would get, and this is what you would describe as a interleaving of things. Okay. Yeah, it's saying the same thing, but it's another example. All of the strings on the left-hand side are all of the valid orderings. And it's important, I'm calling them strings on purpose. I'm about to start talking about regular expressions in finite automata. Now the question is, how do we take something like this and then turn it into one of these strings? Well, first thing to recognize that this is a dependency graph. It's a directed graph. And it kind of looks suspiciously like a finite automata that would result from converting a regular expression into a, say, deterministic finite automata. And then you look at it a little more, step back, and within the circles, I have task A, task B, task C. A finite automata typically has the characters on the labels on the transitions themselves, or the arrows. And then within the circles, those are actually given numbers and called states. And then you remember the day that you skipped when they covered the shuffle operators. And I'm going to talk more about that. The day in computer science class. All right, so this is a breakdown of the different kinds of finite automata. I'm talking about finite automata within the subject of formal languages and computer science. It's literally just a directed graph. The edges are labeled with symbols. The states are numbered. So I don't have the formal definition here, but the things that are that decorate the edges, the labels, that consists of the alphabet. So typically A through Z. You can add some other symbols. And then the states themselves are not explicitly defined. So when you define a regular expression, what you're doing is you're defining the transition among states. You're not defining the nodes themselves. Those are implied, as opposed to other ways that you can define directed graphs. You would define the node, and then you would define the edge, and then you may have a label on the edge, you may not. But we're taking sort of a different approach. So deterministic finite automata, those are typically what people think of when you consider finite automata. It is deterministic, meaning it is explicitly defined. Every transition is defined, even down to, like, if you were trying to figure out if a string was acceptable in this DFA, then it would not only would it not so you don't define it not being accepted by it just not going anywhere. You literally have to define what they call sync state. So it has to go somewhere, but whether it's accepted by the transition or not determines whether you proceed through a path from a start state to a final accepting state in the DFA, or if you go into a sync state, and then that, of course, indicates that you're dead in the water. Non-deterministic finite automata is a class of finite automata. It's equivalent to DFAs. It has something called an epsilon transition. And these are transitions that just happen automatically. And this is where you get a way to implicitly define a finite automata. And it necessarily compacts the state space. And there's an algorithm called subset construction that would allow you to go from non-deterministic finite automata to a DFA. Now, if you think about a string, if checking a string, I probably should have had an animation for this, but if you have a string and you wanted to know if it was accepted by this DFA, or if it matched a regular expression, okay, then with DFA, I said you have actual sync states where the execution path would go in if it was not accepted, if there were no transitions on the symbol that's currently being considered. In non-deterministic finite automata, it's sort of like the multiverse thing, where you've got all these like parallel worlds where due to the epsilon transitions, which just happen automatically, you're considering a single string, but you're considering it over multiple potential acceptances. So you're testing it in multiple different universes. The universes in which it is not a valid string, they just kind of disappear. So they kind of die on the vine. There's no sync state. You don't know what happened. You just can imagine that that universe just collapsed and went away. For the universes where, so far so good, the string is being accepted and there's an actual path, then an accepted string will eventually land on an accepted state. And it's sort of like the Schrodinger's thing where things collapse. If a string is accepted within a non-deterministic finite automata, then the whole thing collapses down and you end up in an accept state. I don't know if you can implement this in quantum computers. I really don't understand that stuff, but the only way you can't really emulate actual non-deterministic finite automata on hardware. It's more of a thought exercise, but you can kind of do it because you can just have this massively parallel machine checking a string on this massively non-deterministic finite automata. But you're actually in one universe and you're actually checking each of these things in parallel. But the non-deterministic finite automata gives you that notion of the parallel universes or independence among different things that you're checking. Parallel finite automata as an additional transition, it's called a lambda transition, and this is where the shuffle operator comes in, because the shuffle operator adds that lambda transition. Now, one thing to note, if anybody's interested after this, parallel finite automata are equivalent to binary Petri nets. And there's a paper by Stotz and Pugh in 1994. It's called Parallel Regular Expressions, and this is kind of what kicked me onto this whole thing. But there they talk about, their focus is on Petri nets, and they go through and they explain, what a Petri net is, what a lambda transition is, and how you can define a Petri net using what they call a parallel regular expression, and then you can transform that parallel or convert the parallel regular expression, which is just a regular expression with the shuffle operator, into a parallel finite automata, which is just an NFA with the additional lambda transition. Okay, and what the shuffle operator implements is more of an interleaving of languages. And I'll show you some more. I need to start moving faster, I think. So in the deterministic finite automata, you've got the operators. I think many people are mostly used to with the Perl regexes, and these mean the same thing. There's concatenation, which is usually implied by just symbols being next to one another. So like you write a string and those are concatenated. We also have the concatenation operator, which is the dot. So it's the same thing. It's just concatenating symbols into a string. There's union, which is the or, and then there's the clean star, which is you get 0 or more. The regular expressions in the computer science world don't have anything else. There's no saying I want 0 or 1. I want there's nothing like we have in the Perl regular expressions that define some limitations on I want 5 of these things or I want 0 or more. There's nothing like the plus, that sort of thing. So this is what we have when we're talking about DFAs and formal languages in the computer science world. Non-deterministic finite automata doesn't give you anything else. It just gives you that additional epsilon transition. So you have concatenation, union, clean star. With parallel finite automata, you get concatenation, union, and the clean star, but you also get the shuffle operator. And I mentioned again here, it's equivalent to a binary Petri net. There's probably a lot more information online about Petri nets than PFAs. Let's see. So one thing to note is valid operators in regular languages are necessarily closed. They call it closed in under regular languages. And what that means is if you want an operator, like say the concatenation, to be considered a regular operator within a regular language, the concatenation of 2 strings, or we can say even 2 languages, regular languages, has to result in itself a regular language. there's a lot of things you can do with regular languages and combine them in all kinds of ways that require, say, a push down automata to accept them or to detect them. So you could very easily combine two regular languages in a way that would either make them a context sensitive language or context free language or even some sort of universal language. So when we talk about regular operators, we need to make sure that it has certain properties. One of those properties is that it results in a regular language. And the shuffle operator does this. And I am kind of on a hunt for other operators, but it's not super easy to find. So I may need to dig a little deeper into that. But the shuffle operator, I meant to put a picture of this book. The book that I still have this copy from many years ago, and it's pretty worn because I really dove into it. It was an introduction to automata theory, languages, and computation by Hopcroft, Motwani, and Ullman. And Hopcroft and Ullman recently just won a Turing Award for awk, by the way. I don't know if y'all knew that. But in any case, in this book, they don't even formally cover the shuffle operator. In fact, they bring it up in a assignment in the back of the book. And I didn't even know that until I read that Stotts and Pew paper many years ago. But I thought that was interesting that I would love to see some kind of paper information on what are all of the regular operators, because as we can see with the shuffle operator, it's useful for something. It's not, it may not be immediately obvious, but if you can apply it to other things and leverage it for some interesting things. All right, so this is an example of a shuffle. So we have two languages. We have string AB, and you can consider that a language, a regular language. It's just the string AB, and then language 2, which is CD. Now, if I were to shuffle these two, then that means that the resulting string, the resulting valid strings of the combined or the shuffled language would necessarily have to include a string that is valid in language 1 and language 2. So that means that any valid string has to have AB and CD, but it says nothing about how those strings need to be ordered with respect to the two different languages. The valid language within each language obviously has to remain totally ordered, but the ordering between the valid strings of the two different languages can be interleaved in any order. And I think hopefully this looks exactly like what we were talking about before. How do you take something that is parallel and correctly enumerate it as sequential? Well, this is how you do it, because it's really just an interleaving. A and B have to happen in that order. C and D have to happen in that order. But you also have to create a single string, which is just a single line of execution, let's say, and then present it in this way. So you can interleave the valid strings. Okay. So regular expressions, deterministic finite automata, and non-deterministic finite automata are equivalent. And the flat module that I created, all this is all well-known stuff. But it implements converting from regular expression to NFA. The way that I do that is I basically just use recursive descent parser. I create an abstract syntax tree, and then over that AST, I do something called Thompson's construction, which is you literally just traverse the AST and you're building out the finite automata using certain elements of graph connections. It's an interesting. I suggest you look it up. I love talking about it, but this is not the time or place. To make it easier, it introduces epsilon transitions, and that just gives it some wiggle room as far as the types of elements that it is using to construct this directed graph. You can also you can convert from an NFA to a DFA using something called subset construction. That's another interesting algorithm. It basically just finds all identical states by building buckets, and then once it has all these buckets built, all the non-determinism is gone. It collapses the non-determinism into a deterministic finite automata where you can execute it sequentially, or you can validate a string sequentially over it. Now, one thing that I necessarily have to do is once I have a DFA, I need to be able to generate valid strings. So I don't know ahead of time what a valid string for this DFA is. But what you can do there is just do a depth first traversal from the start state to an accept state, and then collect the labels along the way. And that is your string. And it works out pretty well. Converting from well, I say shuffled PRE, it's either shuffled or it's PRE. So by converting to a parallel regular expression to a DFA involves an additional step. So that first point actually should be PRE to PFA. I'll correct that before I pass these slides on. But it does the same exact thing. And Stotts and Pugh define a modified Thompson construction element. So for a regular expression AST that has the shuffle operator in it. And that's where the lambda transition gets introduced. Okay, so we've got this PRE to PFA conversion. Now we need to do a PFA to an NFA. Well, back when I was looking into this, they didn't define how to do this, and they didn't answer my emails. So I had to figure out how to do this. Well, how do you do this? What you do is, since all the strings from all the languages necessarily
Sorry, Brett,
need.
you've got 5 minutes for either questions or to finish up.
Oh, dang it. Let me move on. So, okay, this is an example. Going from that dependency graph that I showed in the beginning to a parallel finite automata. This is what the NFA looks like. So you can see it's starting to look like if you take a path from start to finish, which is the circle 17 with the double rings, then you can enumerate valid strings from this. This is what the DFA looks like after subset construction. So a lot of times we minimize it so we get something a lot neater. So given that original graph and then that list of all the valid orderings of the execution, we can generate that from this as long as we go. And if we take all paths from start, which is state 0 to state 15, you will get all of those strings. All of those strings are valid in this regular expression and this DFA. All of these strings and paths are also sequentially consistent. Therefore, you can define your program concurrently using this parallel regular expression. So the original execution path that I showed in the beginning can be defined using this regular expression where it's ABC shuffle. I say and ABC and XYZ. I say I need ABC to happen and I need XYZ to happen. That shuffler, the ampersand, implies that there's an independence between those two languages. But I can get, if I needed to go from this parallel, what's the parallelism that's implied in this parallel regular expression, to a sequential string that is valid for both of those for both of those threads happening, then I can use the process described to enumerate all the different ordering of execution. This is a PFA, an NFA, and a minimum DFA, just showing that you can do the same thing whether if you have the or the union operator in there, and that's considered a finite language. Let me see something here. Thought I had. So one thing I wanted to note is that I haven't shown any examples with the clean star. The reason for that is the clean star admits cycles into the DFA, and that basically creates infinite languages. I haven't really looked much into that about how to handle that or how that would benefit what we're talking about here. So getting all the way to how do you take this and then use it to write something in a short shared memory sort implicit way? Well, what you can do is you can create this plan. Well, I'll get back to that. What I'm showing here is this is what Perl gives us in terms of, our SMP. I probably should have had this all the way at the very front. But going back to the original example, ABC, XYZ, you can see that within one CPU, you've got the global shared memory. Each node is a subroutine that can have its own state. And then using this module, Subgenius, that I have, that's a joke name. But
1 minute.
oh, so I need to stop for questions. Is that what the 1 minute is, or do I need to stop?
1 minute for questions.
Oh, there's only 1 minute for questions. Okay. Well, let's see. Let's jump ahead. I might have to take questions some other time. This is an example of using a parallel regular expression to define in what order and how you want your subroutines to get executed. I've got tools that will help you use this. Well, I was trying to get to, all right, do I have time to run the JAF?
Can you do it in 30 seconds?
Yeah.
I think this should be an open invite to Houston Pearlmongers in July.
Sounds good to me. All right.
Excellent idea.
Let me open this up real quick. All right. So this is a program that's using Subgenius. I have the PRE here that defines JAF. And then basically I'm compiling this parallel regular expression that defines the order of operations into a sequential plan. And then I've got the subroutines defined below here. And it's taking advantage of the global memory and demonstrating use of the scope, the ability to pipeline scope. Anyway, all right, where did I want to go? All right, open questions. I want to see what it looks. I'm going to be looking at what it looks like when fork is introduced. What gives us when we treat subroutines statefully. How can we use this to do something like related to async await or futures? How can we use infinite languages as a plan? I've got a run loop or a driver within this module, and then I've got some utilities in there that help you write it and basically dump, what the underlying finite automata is. But in any case, check out the module. I've got lots of stuff written on CPAN about it within the pod, and I plan on continuing to work through this. So anyway, sorry I went over. I've spent too much time on the background information. Do we have time for any questions, even one?
We do not.
Take them in Slack.
But there's a
Thank you, Brett.
BOF slot open tomorrow. Thank you for coming.
Yeah. All right. Well, I'll see about doing that. Thanks, guys. Sorry we
Thank
went
you.
over.